Do you see my full screen?
Yes, perfect.
Great. All right. I'll start then. So my name is Neil Dunraj. I'm a PhD student at University of Southern California, aerospace and mechanical engineering, though I focus in robotics. And I'm also part of the Center for Advanced Manufacturing here. So we focus on a lot of cool problems. Specifically, how do we use robotics in really hard manufacturing problems? So I'm a fifth year PhD student. Hopefully, I'll be graduating by the end of this year. And today I'm going to talk to you about like some of the research our lab has done. I've titled this talk "Bringing Human-Aware Decision-Making to Robots for Collaborative Manufacturing." So recent advancements in the development of human-safe robots has made it possible for humans and robots to collaborate closely, right? And this is really useful for automating manufacturing processes, especially producing a wide variety of products in low volumes. This could be like assembling small batch satellites, assembling custom order vehicles. And the question you might be asking is, why do we want human-robot collaboration in manufacturing? I mean, we already have robots in traditional automation where we have assembly lines. Well, human-robot collaboration can increase human productivity and value, right? How I see it is humans can perform tasks that require like advanced dexterity and critical thinking, and robots can do menial, supportive, ergonomically challenging, and repetitive tasks such as part retrieval, fixturing, fastening, things that usually take up like 80% of the tasks in like let's say an assembly operation. So the video I just kind of showed is a assembly cell that we designed here, where we have a mobile manipulator that does all the part retrieval and part retrieval tasks for the human, so that the human can actually focus on the really hard assembly operations. And we also have an arm that does some of the sorting of these parts and gives it to the human when they need it. Now, utilizing these complementary skills is really ideal for flexible, adaptable environments. And so we call this high-mix, low-volume manufacturing. You see this typically in a lot of applications, such as inspection, assembly, service. It's really anything where it doesn't make sense to have a traditional automation line. Instead, it makes more sense to have these like robot cells that kind of focus and specialize on specific tasks. We need them to kind of adapt. So this is just a video of a company in London that is using this sort of like these micro factories to generate these like autonomous vehicles, and they use like a very similar strategy. Now, what's the challenges? The challenges is in these sort of high mix environments, we can't do all the effort of having like precisely fixtured robots with precise calibration. So what is going to happen is we're going to have task execution and duration uncertainty, and this is going to result in unexpected contingencies. So if we want to have this paradigm, this human-robot collaboration paradigm, we don't want robots failing and just stopping their execution. Because if we do that and we just utilize humans to address every failure or contingency that happens, this becomes really inefficient. And this is really why we're not seeing robotics in these sort of high-mix environments. The other challenge is there's going to be a lot of uncertainty in the human's high-level decision-making process. So if the robot's not aligning with human preferences, this can lead to a negative perception on the collaboration. This is going to decrease teamwork efficiency. In contrast, if humans are assigning goals to the robot and they're not optimal, this can also lead to inefficiency in task execution. So we need to think about how we promote this synergy between robots and humans, where we're incorporating the human's decision-making process. So this challenge is like really evident in multiple human-robot collaboration domains, and we've explored a lot of these from like satellite assembly to ATV assembly, and we realized that we need to account for contingencies that could occur, and then also the human's preferences. We see this is really present in a lot of complex manufacturing domains, like this ATV assembly that we've examined. So essentially, what do we need? We need an effective dynamic task assignment algorithm for these human-robot teams so that we can kind of handle these task failures and these task delays. And you can kind of see that if humans or robots are working together in a specific assembly, we need robots to align themselves with the human's preferences and goals so that we can boost the human's productivity. If the human and robot's not aligned, we're going to have serious inefficiencies. So how do we develop this human-aware AI, where we handle these uncertainties in collaborative manufacturing? There's many aspects that we need to consider, right? There's safety, there's motion prediction, but the two that I really want to highlight, and this is kind of some of the research we've done in this lab, is one, how do we do contingency management during the task assignment and scheduling phase for human robot teams? And two, how do we incorporate human preferences during the decision-making process? So I'm going to first go into contingency management and the task assignment and scheduling problem. So I want to give some background because I'm not sure what everyone's familiarity is with task planning and task scheduling. But our input is we have a number of agents. These agents are both humans and robots. And these agents can be either busy or idle. We also have a number of tasks, and these tasks also have states. They can be available, in progress, completed, or failed, meaning there's a contingency that's occurred. These tasks all have constraints as well, which comes from the assembly, it can come from the workspace. And we use a hierarchical task network to represent these constraints. So in this example, if we have, let's say, 4 assemblies, these assemblies can be done in parallel. We have this parallel constraint. And for each assembly, we're probably going to have different sub-assemblies that we have to assemble. And so these sub-assemblies each need to be done in sequence. And some sub-assemblies don't have an order, but they can't be done at the same time. So we use this HTM to encode the entire constraints for this task planning problem. Now the objective is to minimize the make span, the time it takes to complete all the tasks. We need to determine the task assignments and schedules for human and robot agents. So there's many ways to do this, but something that's been working really well in our lab is we've been using constraint satisfaction solvers to solve a mathematical program so that we can generate these schedules. So we've been using different operation research tools to generate these schedules. Now, what does contingency management really look like? Well, first let's define a contingency. So contingency in our case is literally just an unexpected circumstance that's been faced by the agents during execution. And we've done a lot of work in these robot assembly problems, such as robot screwing of this ATV assembly. We've done robot teams for assembling small satellites, and this is sort of the different contingencies we noticed. For example, screws might get stuck because there's uncertainty in perception, parts might not be present, and what we notice is in typical robotics programming fashion, if a contingency occurs, the cell just stops. And we need to, as us, the PhD student, we have to step in and kind of reset the cell so that we can restart the assembly process. So in the event of a contingency, humans adapt by adding recovery tasks to the plan themselves. The question to ask ourselves is, how do we create an autonomous framework to react and account for these contingencies? Because we don't want robots also to just stop and wait for the human. There's 2 ways that we kind of think about it in our lab for managing contingencies. One, if we know that the robot hasn't seen contingencies, then we need to reactively manage the contingencies. The robot needs to determine the procedure for recovery. And in manufacturing, most likely this is going to come directly from the human. The human has to specify this procedure. And if the robot has seen this contingency before, we need to autonomously generate a plan to recover from this previously seen contingency. The other way to think about this is if we have knowledge of these contingencies, such as the probability of the contingency occurring, what's the effect of the contingency on the task planning problem, and how to recover from the contingency. The question we want to ask is how do we proactively incorporate this information and account for these contingencies when we're generating a task plan. We talked about challenges in task execution and duration uncertainty, and there's also going to be challenges in incorporating uncertainty in the human's high-level decision-making process. So, robots may not align with the human preferences, and this is going to lead to a negative perception from the human. And also, when humans assign goals to the robot, if the humans aren't considering optimality, this is going to lead to suboptimal performance. So we need to also incorporate humans' preferences in the decision-making process. So these challenges, they're pretty evident in a lot of human-robot collaboration domains. And so we need to account for these contingencies and preferences and how they present themselves in these complex manufacturing domains. So this is an example of a high-mix, low-volume ATV manufacturing assembly. So what we need is effective dynamic task assignment algorithms for human-robot teams so that they can handle task failures and task delays. How do we do this? What we need to develop human-aware AI, which can handle uncertainties in collaborative manufacturing. And so I think given the time constraints, I'm going to talk about the first one. How do we do contingency management during task assignment and scheduling for human-robot teams? But another thing to also consider is incorporation of human preferences during decision making. So let's start with how do we manage contingencies. So I'm going to go over some background just in case people aren't aware of task allocation and scheduling. For task allocation, the input is we have a number of agents. These agents are going to be both humans and robots. We're also going to have a number of tasks, and these tasks are going to have states, whether they're available, in progress, completed, or failed. Lastly, these tasks are going to have constraints and how they're going to be accomplished. And we use an HTN to describe these constraints. So you can see an example HTN here. So let's say our human-robot team needs to accomplish 4 assemblies. These assemblies can be done in parallel, but each assembly is going to have its own subtasks, such as making the sub-assemblies. And each sub-assembly is going to have a sequence of tasks that need to be accomplished. And so in HTN we use HTN to encode these constraints. Now, the objective our initial objective in this problem is how do we minimize make span, the time it takes to complete all these tasks. So we need to determine a task assignment and schedule for these human and robot agents. Specifically in this lab, something that we found works really well is we've been using constraint satisfaction solvers, where we model the task allocation problem as a mathematical program, and we use that to generate both task assignments and schedules, which minimize a make span. So it generates a schedule. You can see an example below. Now let's talk about contingency management. What exactly is a contingency? In a general case, it's just an unexpected circumstance faced by agents during execution. So we've done a lot of these assembly problems here in this lab, and we found different contingencies such as a screw gets stuck or parts are not present. This can kind of just stop the robotic assembly cell completely, and we as a PhD student would have to step in and sort of reset the cell. So in the event of a contingency, humans usually adapt by adding recovery tasks to the plan. What we need to do is to determine how can robots use an autonomous framework so they can react and account for these contingencies. Now there's 2 ways you can kind of think about contingency management for robotics. There is reactive contingency management. So if the robot hasn't seen the contingency, then it will need to reactively manage the contingency by determining the procedure for recovery. So in the manufacturing application, this is most likely going to come from the human. However, let's say we have knowledge of these contingencies, the probability of it occurring, the effect of the contingency, and recovering from the contingency, then we want to ask ourselves, how do we proactively incorporate and account for these contingencies when we're generating the task plan? So that if a contingency does occur, the effect of it is minimized. So let's talk about how we reactively manage contingencies. So in our lab, what we've done is we've explored reactive contingency management by using human feedback in large language models. The objective is to enable the robot to recover from contingencies using human input, where we want to have a minimal impact on the spin. The second objective is we want to minimize the amount of human intervention and need for human expertise. We don't want humans to do too much programming, task model editing, etc. There's two challenges we need to kind of think about. One, how do we incorporate contingency recovery methods by editing the task network? And if we do this directly using domain experts, this is going to be tedious. The second challenge is, yeah, we could use LLMs to convert human instructions directly into a task plan. The problem with LLMs, especially in the manufacturing setting, is there's no sense of feasibility or optimality. So what's the key idea that we found? What we found is we can actually leverage the combined strengths of LLMs, HTMs, and classical planners together. LLMs allow us to convert an expert's human's natural language input into a recovery procedure. And if we teach the LLM how to integrate a recovery procedure into an HTM, we found out that actually works much better in successfully generating recovery task plans. Once the LLM is generated in HTM, we can then use a classical planner to generate the optimal task plan that respects the HTM constraints. This also gives an additional benefit that we can store the LLM output and the HTM. And if we find a similar contingency, then we can use the LLM to just directly generate a similar recovery procedure without getting human expert input. And all we need to do is just validate it with the human expert. So how exactly do we do this? We just need to do a little bit of prompt engineering, to be very frank. And how we do this is we give the LLM a structure and how the HTM can be modified. We do this by predefining code primitives, which are just functions that the LLM is allowed to use to edit the HTM. This is just giving more structure to the LLM on what it can and can't do. We also give information on the robot cell and the current task state. And lastly, we give example recovery procedures that either are predefined or something that's been encountered beforehand. And the LLM can use this as a template. So this is all a prompt that we give the large language model. So when a contingency occurs and it has been seen by the human would then give an instruction to the LLM on how to address the contingency. And it's going to use the previous prompt and prior experience to then generate the recovery procedure as code. And that code is then used to create an HTM, and we input that back into the task plan. So what that might look like is, let's say the robot is doing a screwing task and the screw gets stuck. The human would just give instruction of the robot should unscrew the screw, remove it, remove the stuck screw, pick up a new screw, and reattempt as natural language. We saw that the LLM can generate this as code, and this generates a new HTM. And this gets passed into our constraint solver, and the robot cell executes the new task plan. So this is just an example of how this contingency would be handled reactively using LLMs. So some just results to talk about, some insights from this is LLMs can utilize this HTM structure to successfully convert natural language to a recovery procedure. And this proposed reactive contingency management method actually results in smaller learning spans in comparison to just directly relying on domain programming experts to code the recovery procedure. Lastly, we saw that LLMs have, given the structure, we found that at a minimum, we had an 80% success rate in generating HTM recovery procedures on the first attempt. And if it didn't do it on the first attempt, it was very easy for a human to correct the LLM and change the task plan. So this actually works really, really well in very complex assembly tasks. Now let's talk about proactive contingency management. A lot of times in manufacturing applications, we're going to have prior information on which tasks can result in contingencies. So we might have a model of this. And this gives us probability of a contingency occurring, the effect of the contingency on the task plan, and how to recover from the contingency. Now the question we want to ask is, if we know all this, how do we proactively incorporate contingency information into the task allocation process? So what we've done in this lab is we've determined like a new algorithm, which we call contingency-aware task allocation. We do this via hindsight optimization. So let's update our problem description. Let's update our problem description for the task planning problem, where we also have a task execution probability model. This lets us know the likelihood of the robot performing a task successfully or resulting in contingency. We also have a task contingency function, which returns us the recovery procedure already incorporated into the HTM. So we're assuming that the human operator has given this information to the system beforehand on how to modify the HTM with the new recovery procedure. So we can think of this as a problem of we need to determine a series of states and actions. So we can use a multi-agent Markov decision process, where the state of the entire system is just this factored representation of all the task states and the agent states. And so each state is just a decision epoch when a new task becomes available for agents, or an agent has finished a task and is ready for a new assignment. An action is just then a task assignment or a no operation action that the system can take. So it's just a joint action. And then we can define the transition probability function as just a joint transition of going from one state to another after an action is taken. And we derive this from the task execution contingency probability that I mentioned earlier. The cost of going to a state is just then the accumulated time taken to reach that state. So the cost to get to the goal state is then just the make span of completing all the tasks. Our objective then is to compute a sequence of states and actions that minimize this expected make span. So this is how we kind of formulate this task planning problem into a Markov decision process. So our objective is, how do we enable proactive task allocation for human robot teams, where we can consider this task execution failure and task delay uncertainty proactively so that we can minimize the expected make span. There's two challenges we need to kind of think about. They're combinatorial challenges. If you think about formulating the state action as constructing a tree, we're going to have two combinatorial explosions coming from the multi-agent coordination and planning under uncertainty. So solving this joint problem is like very computationally intractable. So what's the key idea to solve this? The key idea is we hierarchically solve the problem. So the key insight is, for applications where we have strong task dependencies, so we see that a lot in manufacturing, where the coordination decisions are dominant, we need to later consider the effect of uncertainty. So what we can do is we can decouple the problem and consider a hierarchical approach. At the lower level, we would be coordinating multi-agent decisions. And at the higher level, we would reason about uncertainty and task execution completion. So at a high level, this is how we kind of implement this key idea as the following. The upper level of our approach is going to sample different task execution scenarios that the multi-robot team may face. So these are just different contingency scenarios. Our lower level then takes this scenario and solves a multi-agent coordination subproblem. And this generates a new task allocation and schedule. We can transform the schedule into a sequence of states and actions from our Markov decision process formulation. And what this allows us to do is, from the state action sequence, we can then sample additional task failure contingency scenarios that we can then evaluate. By iteratively doing this and by merging these new scenarios, these schedules, and these state action sequences into a search tree, we can then do backpropagation and figure out the best task allocation. Now, the question that we need to ask ourselves is how do we choose which scenarios to evaluate and how to evaluate them? So our second key idea that we kind of came up with is we can create an explicit framework to reason about these different contingency scenarios. So consider, we initially generate an optimistic schedule, optimistic task allocation where everything goes correctly. We can then sample a likely contingency that might occur while executing the scenario. And in hindsight, we can explicitly evaluate how to recover from the contingency. So what's the best task allocation for recovering from the occurred failure? How do we mitigate the contingency if the failure was known in hindsight? And then what's the best task allocation for preventing the contingency if the failure was known in hindsight? So this gives us this hindsight optimization algorithm that we've come up with. From our initial state, we use our lower level solver to generate an optimistic schedule. So that's the green state action sequence. And then from that, we sample a contingency state that could occur while executing the schedule. So for an evaluated contingency, we then generate 3 schedules for each reasoning process. How do we recover from the contingency, which is the red state action sequence? How do we mitigate, which is the blue state action sequence? And how do we prevent the contingency, which is the yellow state action sequence? We keep doing this, and we keep merging these new state action trajectories back into the search tree. And we do back propagation to then find the best cost task assignment, the lowest cost task assignment. And we keep doing this at each decision epoch where we run this search and we generate the lowest cost task assignment. And this works pretty well, is what we found. Let's discuss some key insights. By explicitly reasoning on how to mitigate and prevent contingencies, what this is letting us do is it allows us to explore alternative good task allocations. And then by reasoning over recovering from these contingencies, we can determine the expected make span for each task allocation. Essentially, this framework allows us to effectively build a search tree by evaluating scenarios in hindsight. So we don't have to build that combinatorial explosive tree if we just did a brute force method. You can also see that we don't need to consider every possible task assignment. All we need to do is just sample likely contingency scenarios and determine good task allocations for those scenarios. And then the search tree just gives us a structure for determining the best task allocation that minimizes the expected make span. So the results of this, we found that this gives us up to a 15% improvement in expected make span for these assembly inspired domains. And we found this approach is especially effective for failures in assemblies which require complex recovery tasks. Essentially, failures that require global replanning. So for an example, such failures could be if a robot damaged a part or something went missing in the assembly and we need to do disassembly and try again. This is where using this hindsight optimization gives us gains and improvement for this expected make span. So this is where we found proactive can really help in getting these gains. And this is really useful for manufacturing applications because that 50% expected make span is a lot of money that you can save when doing this. So I'm going to do a quick highlight on how we can incorporate human preferences, just give a system overview, and then we'll go from there. So the second thing I want to talk about is how do we incorporate human preferences during decision making. Now, humans are going to have preferences on how they will complete their task. And if we want efficient teaming to happen, we need robots to kind of complement humans and adapt to their preferences for maximum efficiency. These preferences can be highly individualized. So we did some work in the left, as seen in the left figures, so this is our prior work. We created this model airplane assembly task, and we wanted to examine uh, what sequence of tasks humans prefer. And we found that some users prefer to complete high physical effort tasks first, or high physical effort tasks like this propeller assembly later in the schedule. So they have these sort of preferences based on high physical effort, high mental effort. Furthermore, there can be contextual and situational information that can affect the person's preferences, such as in the right image. The human expects a delay in parts that might be required that day for assembly tasks, and the user might prefer to delay all the associated tasks. So, because these preferences may not be known beforehand, we need a human in the loop planner to elicit these preferences from the human and incorporate them into the task plan. So we've done a lot of work in how do we elicit these preferences and incorporate them into the human in the loop task scheduling. And I won't have time to kind of go into that work, but perhaps you can kind of reach out to me if you guys are interested in how preferences can be incorporated. So I'm going to skip these slides, but some of the insights that we kind of got from this work is a human in the loop framework is able to efficiently elicit and incorporate preferences for human robot task scheduling. And we came up with this diverse constraint programming approach, which allowed for very complex preference specification using first order logic. And lastly, we again use large language models here. And we found that they were very effective translators of preferences into mathematical constraints, which is really useful for us. So you got to hear the contingency side of this talk, but the big question I want to kind of leave you guys with is, why am I telling you about contingency management and preference incorporation? So many people think that we need to have this like perfect generalist robot that can fully perform all these hard manufacturing tasks that humans are currently doing right now. So robots are going to completely replace humans. Humans don't have to do these hard tasks. However, we're still pretty far away from achieving that. So instead of waiting for robots to become perfect to do these hard manufacturing tasks, what I'm thinking, what a lot of people are thinking, are let's use them now alongside humans, where they might still make mistakes, but we just need to provide a framework for robots to recover from these mistakes, these contingencies. And this will allow humans to perform much more value-added tasks. Now, the key to this, the biggest insight that we found is like large language models will kind of help bridge the interaction gap between humans and robots. So we can use large language models to allow just regular human operators to both program these robots, give instructions on dealing with complex contingencies, and even incorporating preferences. If we handle contingencies properly during task-centered scheduling, this allows for much more robust systems. So this utilizes the human's value and time without wasting it. And so we can allow humans to do these value-added tasks. And lastly, if we incorporate human preferences during decision-making, then I believe humans will be more willing to collaborate with robotic systems. And an aligned, efficient human-robot team is going to lead to a much more efficient task execution. Thank you, and I'll take any questions.
Thank you so much. So I'm quite interested about the generative AI that you mentioned at the end of the talk. So I keep on asking myself, how can we incorporate AI to a manufacturing site where we need robotic systems and human to work together? So do you think it's an issue that we could have too many cameras, too many sensors, too many microphones, and too many data?
You think it's an issue?
How do you think? Yeah, do you think that would be an issue? Because for us right now, we are working as a team with in multiple professors' lab. We are doing, each of us are doing specific task, and we basically prepare our own computer or laptop or like an embedded system for with probably two cameras, one microphone, three sensors from each group. So when we integrate everything together, it's like multiplying the amount of computers, cameras, and sensors. So I understand that we should integrate them and reduce the amount of them in the future, but to be able uh, to make the AI behave like human, we probably need this many amount of sensing and detecting. But it's such a complex environment in such a small space, not to
Right.
mention about the whole factory. So, what's your opinion about having so many IT stuff in one small area?
I think the system infrastructure that we need to like get that running is a lot, and that's certainly a barrier for getting these like generative AI, successfully working. So I'm sure, hopefully, a lot of people have seen like diffusion models and this generative AI for like teaching skills for robots. We need this multimodality for it to happen. It's a little difficult to reduce it. So hopefully, if you think about it, humans, we don't have these like complex multimodalities, just like LiDAR, RGB depth cameras. We can do it pretty simply, but I think right now we do need those sensors to kind of get these robust systems up and running. But I've seen a lot of applications where people are using pretty cheap sensors and getting like very successful results. So these like new imitation learning algorithms have been doing a really good job of using like cheaper sensors to get this to work. So I think we'll be fine.
Thank you. So, is there any questions from the students?
Yes, Professor, can I ask them?
Yes, please.
It's nice lecture, Neil. What are the incorporation of safety protocols in this model? How it deals with some safety protocols related to human-robot collaboration?
That we consider this. So this presentation was more about like higher level decision making. So like more of like task allocation. So we I didn't talk about the safety protocol.
How it
We've done
integrates
prior.
how it integrates the safety protocol in the task replanning?
So the safety, how it would be done is that's just another contingency, essentially, right? So what we've done robotic assembly of satellites with humans. We would have cameras that did human motion prediction, or human tracking with human motion prediction to see where humans were going. And if humans were going to enter a work zone with a robot that's not collaborative, then that work cell would be stopped. So that's something that we did implement. And that is a contingency. It's not a modelable contingency, so it's not something we can be proactive about. But it is something we can be reactive about. So if we have a contingency where a human comes in, we did kind of encode these instructions of just the robot would stop and wait for the human. So that's like the simplest way we like kind of dealt with it. A future work that we all are kind of like working towards in the lab is how can we do more sophisticated intention prediction, right? So this intention prediction kind of gives us that proactive safety of predicting what the human's going to do next and trying to be away from that with the robot. So that's kind of how we kind of looked at it.
Thank you.
Any other questions from the students? Go ahead.
I would like to ask, when an accident occurs, how to decide which robot or human will handle the situation?
When what occurs?
Like an accident.
When an accident occurs.
Yeah. Like who does what first? Yeah.
The constraint solver, like the classical planner, determines like the new task plan, right? So that's kind of the nice part of using LLMs to kind of generate a new hierarchical task network. So that just specifies the new constraints. The constraint satisfaction solver just generates a new task plan for the entire team. And so the entire robot team then just sort of adapts. So let's say we have like a large, like the ATV robotic cell. We have a lot of robots, and an accident happens, and one robot is disabled. We would tell the LLM that this robot is disabled, and so that would remove nodes from the task network that robot can do the task, and we just input that HTM back into the constraint solver, which just generates a new plan. And we're not trying to generate a completely optimal plan. We're trying to generate something near optimal that we can determine quickly in 10 to 20 seconds, and then deploy that out to like the subgroup that's been affected. So the constraint solver kind of just generates a new task plan, which we then deploy back out, so that the robots kind of just adjust accordingly until the human can go and fix the accident. So that's kind of how we're doing it. And so again, this kind of aligns with our reactive contingency management framework.
Okay, thank you.
Good. Thank you, Neil. Thank you so much for today's talk.
Thank you, and thank you for bearing with the internet issues.
Well, no issues. I hope really soon we can visit USC, and hopefully we can meet and talk more about research
Yeah, of course.
or anything else. Lakers, Dodgers. Okay, cool. Thank you so much. Thank you, Professor Chen. We'll see each other again next week.
Yeah, hopefully next time we will not have this issue.
Yeah, hopefully, yeah, we can get more familiar with this. Okay, thank you all. Bye bye.
Bye-bye.
Thank you.